Hi guys, welcome back to part 3 of Stratified Sampling. If it's been a while since you watched part 1 and 2, let me just quickly recap what we did. In part 1, we talked about stratified sampling in a very high-level conceptual sense. We created a data set which represented our population. In part 2, we started to study that population, and we applied simple random sampling of a sample size of 50 to that population. You see the code actually on the screen. Actually, the second line of code is what generated the samples of size 50. We created 1,000 of those, and we also specified what we were interested in learning about. And what we wanted to learn about ultimately, don't forget this in the study, was mu, the true average height of people in this population. And we actually know exactly what that was because we created the population. But from a realistic standpoint, you never get to know what mu is. You always estimate it with x bar. But how you arrive at this x bar does have an impact on how well this estimates mu. So how you get the x bar, what I'm talking about is how you take your samples. So if you take a simple random sample like we did, you'll end up with a good estimate for the mean, for mu. How good? Well, we can measure how good, how precise that estimate is by getting the variance of the estimate. So here, based on our 1,000 simple random samples of a size of 50, we ended up with an estimate, an average of the averages of 71.97, but more importantly, with a variance, and let's say this is the variance of the x bars, and this is an estimate of the variance of the x bars because we didn't generate every possible sample, of 4.60. So now what I'm saying to you is, in stratified sampling, we should be able to improve on this precision. In other words, this number should go down for us. Why? Well, I set this up so that the two strata, males, females, were quite homogeneous with respect to the variable that we're trying to study, which is height. Okay, so let's see if this actually happens in practice. Okay, so let's generate some stratified samples now. So now this might get a little more involved. So we're going to do proportional stratified random sampling, as I mentioned in part 1, using gender as the strata. So first, let's just take a look at how many, let's just remind ourselves how many males and females we had. So the population is a 60-40, perfect 60-40 split. So you have to have some idea, as vague as that may be, of the proportional, size of your strata from your population. If you want to do proportional stratified sampling, you want to take a sample that is proportional to the mix in the population. So in other words, if I wanted to take a sample of 100 people, I would aim for getting 60 female and 40 male. That would give me a proportional stratified sample. And then from within the females, I would get 60 of them, 60 observations randomly, and from within the males, I would get 40 observations randomly. So I would take random samples within each strata, and that's what we're going to do. But since I chose an N of 50 for the previous case where we did simple random sampling, that's when we didn't split the data into subpopulations, I'm going to stick with N equals 50 so that we can see what the precision gains are if we don't mess around with the sample size. Okay, so how do I know how big a sample I need? Well, let's just multiply these by 50. So I'm going to take 30 random observations from the females and 20 from the males. Okay, that's good enough. Okay, now the process of actually collecting this data. So let's first create a vector called x bar, and just an empty vector. Okay, so that's going to set up. So all the x bars that we calculate from our stratified samples are going to fall into this vector eventually. Okay, so we've just set that up. Now let me set the seed so that you could repeat and get the same results. And then we're going to do the random generation process. So for that, we're going to do a for loop. We're going to generate 1,000 samples again. Okay, and we're going to populate x bar strat here, as you can see, by calculating the mean of 30 randomly selected heights from the first 6,000 rows, which, if you recall, were where the females were. Okay, so that made that process easy. So 30 females as we wanted to achieve. And then if I can scroll to the right, you'll see from the 6,001th row to the 10,000th row, that's where the 4,000 males were. I'm going to randomly select 20 of them, 20 heights. So in the end, I'm going to end up with 50 heights, okay? And 30 of them are going to be females and 20 are going to be males, which is exactly the proportions I want to reflect my population mix. And I'm not interested in the actual genders, because I know I've achieved the 60-40 split, or 30-20 if you want to in absolute terms. So all I want to do is get the mean. So I'm going to get a bunch of x bars. But let me distinguish these x bars from the simple random sample x bars by calling them x bar strat. That's a common notation. So you know this x bar is from a sample, but it's from a stratified sample. Okay, and I'm going to get 1,000 of these. Okay, as you can see here, I'm going to do this 1,000 times. All right, so let's do that. So this is going to generate our stratified samples. Okay, so let's do this. Okay, that took a second. For loop takes a little longer than replicate. Okay, but in this case, we're only doing 1,000. It's enough for us, but not a terrible kind of lift for R. Let's look at, oh, careful. If we look at x bar strat, you are going to see 1,000 x bars. Okay, these x bars were sample averages from stratified samples, not from simple random samples. So here we guaranteed that 30 female, 20 male, whereas in simple random sample, although it's likely to be the same 60-40 mix, simple random samples also going to include plenty of samples where it's not. Okay, so let's see what's the mean of the x bar strat. Okay, all right, that's somewhat interesting, but much more interesting is what's the variability. This is a measurement of the precision. This is a way to look at how precise. You would want this to be as low as possible, okay, given it's an unbiased estimator, of course, and it is. 0.49. Wow. If you recall the variance of just the simple random sample x bar, this is about, wow, almost 10 times lower variance using this technique than using the simple random sample. That's really the crux of it right there. This is what we wanted to achieve when they claim that stratified sampling will produce a more precise estimate, especially when your strata are homogeneous. This is what they mean. That the variability, whether you measure it in standard deviation or your maximum error of estimate or any other way, the variability has decreased dramatically of our estimate by using a stratified sample versus a simple random sample. Okay, it's almost tenfold. Okay. All right. So now what do we want to go? What do we want to do from here? So we got the mean, we got the variance. We can also calculate the standard deviation, and then we could also compare this to the theoretical variance of X bar using the strat method. So let me give you the formula for this. This will be somewhat tedious for me to write. So this is the variance of X bar using simple random sample. We just saw this, okay? And then, of course, if it applies, you can also include the population correction factor, FPC. That's when you're sampling without replacement, and your population, your sample size is at least 5% of the population size. That's a separate thing altogether. This will be a slight adjustment, basically. Okay. So if I could put this aside for purposes of focusing on what we're interested in, we would end up with this as the variance of the X bars using simple random sample. Now, what's the formula for the variance of the X bars using a stratified sampling? Okay, so first we need some more notation. So we'll use n as the total population size. Okay, so you can we'll use n subscript I as the subpopulation sizes. So for the ith population, subpopulations or strata, let me call it strata. Okay, size. Incidentally, we know exactly what all these are. In a moment, we'll be able to attach numbers to it and calculate it. N as the total sample size, n subscript I as the ith sample size, right? So like in each strata, we took a proportional sample size, right? So let me say ith strata sample size. Okay, so we need to distinguish these things. Size. Okay. And then what else might we need? We calculated X bar in each strata. So this is the ith strata sample mean, right? So here we have two strata. So we have n being 10,000, right? N female being 6,000. Let me write 6K. And male being 4K, right? These two should sum up to this. They should be non-overlapping, of course, and distinct, right? We have n of 50. N female, we took 30 to keep with the proportions in the population, and n male we took 20 for the same reason. And then we calculated X bar for the females and X bar for the males. I mean, R did that for us. And then to arrive at X bar strat, as opposed to plain old X bar, we would take a weighted average of these two guys, giving 60% weight to X bar female, 40% to X bar male, and then we would arrive at a estimate of mu, one of these X bars. We generated 1,000 of these. Okay, and we let R do this whole process. Okay, and here is this is the average of the averages of the X bars that we created, the mean of the means, if you will. Okay, so now I want to talk about this guy. So with all this notation, so now we see. So what is the formula? So at least the theoretical formula here. So let me see if I can squeeze it in here and not touch this guy here. So. So we're going to sum from 1 to k. For us, there's just two strata. Remember, k is the number of strata. Okay, here we just had 2. We're going to first get the weights. So this is just a way to get the weights. So for females, it will be 6,000 over 10,000. So it will be 0.6, right? And we're going to multiply the weight. We're going to square this. And then we're going to multiply the weight by the variance of the strata over the sample size taken from that strata. And then if you want to complicate things just a little further, we're going to do a finite population correction just to get a slight correction on this. And you see I'm using the total strata size minus the sample size taken from the strata over the total strata size minus 1. Okay, now if we don't know the true variance of a subpopulation, then we can estimate this with a sample variance from that population. So oftentimes in practice, this needs to be estimated here, this guy. Okay? All right, so this was the kind of theoretical work as far as I wanted to go, and now we can go back and see what the results were. So if you can speed through that if you didn't like that presentation, or pause if it was useful. So this is where I'm going to calculate this. Okay, so here you see I actually have to flesh out the weights. So here's the weight for females. Here I'm looking at only female heights, and I'm going to calculate the variance of the female strata, and then here I repeat this for the male strata, and then I multiply this. I'm sorry, I add these two together. Okay, so let me just copy paste this, and then you can kind of pause and see what I've done, although the code is admittedly not on the screen. It's just a tedious kind of application of that formula I just had on the screen. Okay, so sigma squared x bar, that was from simple random sampling. This one is from stratified sampling. So theoretically, so notice no hat here. That's the variance of the x bars. Theoretically, that's the variance of the x bars using stratified sampling. So you see that theoretically we should have achieved this result, which is almost a 10-fold decrease in the variance of the estimator. Okay, so let's see in practice what we achieved. So to do that, we've already seen these numbers. So we look at the variance of x bar using simple random sampling, the variance of the x bars using stratified sampling. And you see it's pretty close to what we just had up there, the theoretical values. Okay, so what we're doing is getting us pretty close to what the theoretical results in any text on stratified sampling would tell you. And we're actually doing it by taking tons and tons of samples. Okay, and finally, I mean, another way to kind of see the gains in precision is to plot these x bars. Okay, we can make a histogram of the simple random sample x bars, the estimates for mu. Remember, all along we're trying to estimate mu. We want an estimate that's unbiased, so that's a separate discussion. That means that the expected value of that estimate is equal to what it's trying to estimate, and both of these are unbiased, x bar and x bar strat. And maybe arguably even more important sometimes is you want your estimator to have a small error, or to be precise, or to have low variability. It's all really saying the same thing. We see that the precision using stratified sampling produced a much less variable estimate for what we like. So this would be a huge gain to do the study this way. Okay, now let's look at those histograms, and it should be visually clear to you that we achieved this result. So here in this set of code, I'm going to create two density histograms, one for the simple random samples, the 1000 X bars generated from the simple random samples, and then the 1000 X bars generated from the stratified random samples, proportionate stratified random samples. And then I overlay density curves just to pretty it up, but you can see clearly here. Let's look at the two histograms. These were the X bars generated from simple random samples, so SRS, and here are the X bars from stratified sampling. And just look at this. First off, look at where the mean is. It would guess, at least right here. So our mean is, they're both unbiased estimators. The mean of these techniques, the expected value, will give us mu. The question is how quickly, at what rate, and how precise. Well, look at the spread of this distribution versus this distribution. This distribution is between 70 and 75 as far as range versus 65 to almost 80. And both of them, although they do display the bell shape, which is central limit theorem, so check out videos where I show you applications of the central limit theorem, this estimate produces a much more precise result. Okay, so I think we completely understand proportionate stratified sampling, and we applied it using R, maybe spruced up our kind of coding skills in the process. So I hope this was helpful. Be sure to check out my channel and my other videos on machine learning, Excel tutorials, and other data mining, machine learning, and statistics concepts. Subscribe, share, have a great day.